Hello everyone. In this demonstration, we are going to continue on the series of the laser modeling um, demonstrations that we have conducted so far. Here, we are going to demonstrate the moving laser heat source. The work that we are going to be doing is based on the one-dimensional multipulse laser machining of structural alumina evolution of surface topography. Even though the simulation will not be focusing on the evolution of surface topography, and the machining is not one-dimensional, we are going to simulate a moving heat source, which means that it's going to be three-dimensional or two-dimensional, and the laser heat source will be continuous first, and then it will be a pulse mode laser machining process. In the previous demonstrations, we inserted the properties and we basically replicated this article. But for the sake of someone who has not watched them, we are going to pretend like we have not done them, meaning that we're going to start afresh and recreate the model from scratch to properly demonstrate the workflow and the necessary equations that we are going to use. Opening COMSOL Multiphysics. To create the model, we are going to choose Model Wizard. And then to select a space dimension, we're going to choose 2D because we're going to simulate a cross-section of the sample or workpiece that is going to be machined by the laser when the laser is moving across that surface. And then selecting the physics, it is heat transfer in solids, since we're going to be focusing only on that. And then our study is going to be time dependent. In the model builder, the first process or the first step is to create or input parameters. So what we want to input here are the laser parameters and the sample dimensions and the material properties if it's necessary. So first, the parameters, we're going to extract them from this article here. They have been organized in a very nice table. There they are, zooming in or out. So since in the previous demonstrations we added the material properties, we're going to skip this section and move on to the laser machining parameters. What is essential here is that we insert the number of laser pulses, pulse energy, pulse width, the pulse or the beam diameter, the emissivity, heat transfer coefficient, absorptivity, the rest of these parameters until we are at the gravitational acceleration. So I'm going to copy these parameters as they are. This is the number of laser pulses or the repetition rate. So we're just going to include 10, the first number here. And then you move on to pulse energy. I'm using shortcuts to copy, so 1 joule. Pulse width. In other or demonstrations or research articles, they also call pulse width pulse duration. The emissivity of the surface is 0.7. It's a property that we use for radiation heat losses. Now this is a heat transfer coefficient using 10 watt per meter square Kelvin to account for the convective heat losses. Excuse me. Then we have absorptivity, which is 0.25. And then we have the half width of the curve. This is when we account for the phase change, kinetics. We're doing heat transfer there on specific heat. That's a property of specific heat there on the material. Okay. Then we have the reference point of the laser beam. This is where it is on the surface. We are going to change this value, but for now, let's just copy and input it as it is, which is 1000 micron. And then standard deviation of the laser pulse, or the laser beam itself, it is, I'm going to call it XD. I could call it CD if I want, or SD, but it is 100 micron. And then what else do I need here? I think I could take this, the ambient temperature, which is an initial condition, which is 293.15 Kelvin. So those are the laser parameters. Next, let us insert the sample dimensions. So I'm going to expand this. Let me save this. Let me say moving heat source. Let's say heat source. Live demo. So what I would like to insert here, we're going to create a more like a rectangular sample which has a certain thickness and a certain width. But what I would prefer is to link the sample dimensions to the beam diameter so that we do not have a very large sample that is going to give us consume a lot of time when we are what you call computing the calculation. So let's be economical. So the height of the sample, I'm going to call it H1. Let me say diameter of the laser beam multiplied by 2. Yeah, that's the height of the sample or the thickness of the sample. And then the width of the rectangle, let me call that, we want a laser beam to move, let's say we have account for 3 pulses. So let's say d times, let's say 5 times 5 diameter of the laser beam, multiply that by, let it be a multiple of this. Let's see what it looks like. 6. Right? So sample width. I'm making this a multiple so that it's much easier to do other things. So we have the sample dimensions and then we have the laser parameters. And what else do we need? I think we have enough. Okay. So now let's move into the component. Under definitions, this is where you insert the equations that you modify for the laser beam or for the model itself. So the equations that we want here are these equations here. I'm going to expand this equation. This is what we want. We want to insert this here, the laser beam itself. And we want to also insert the pulsing effect. That's what we want to insert the most. So we're going to start with a continuous wave laser beam. So meaning that we're going to we're not going to insert this function yet. So what we're going to do is to try and insert this. So here you have the Gaussian pulse, Pg. It is equal to the absorptivity multiplied by the energy density. So the energy density is calculated by taking the pulse energy, dividing it with the pulse width, and then multiplying that with the beam spot area. And then you multiply all of that with this term here, which represents the laser beam distribution. So in this case, we have a Gaussian laser beam distribution here. So first, we are going to split the PG, which is the Gaussian laser pulse, into two terms: laser energy density and the Gaussian space. So first, let us create the laser energy density. I'm going to call this d ED. It is equal to the pulse energy divided by pulse width times the area, which is pi, times 0.25, which is diameter of the laser beam square, so that's the energy density. Now, what we want here is to now insert the Gaussian space term. We'll call that G space. Okay, so the Gaussian space, it is equals to, I'm going to zoom in more, exponent open bracket negative x, which is the domain that you're working in, multiplied by xr, which is the reference point of the laser beam, square that, divided by 2 times the standard deviation square. So let me just write x minus xr first. We have those terms defined. I'm going to square that. I'm doing this on purpose because it is always tricky to write this properly and with a lot of brackets. And then all of this, I'm going to put it in a bracket. And then I'm going to divide all of this with 2 times the standard deviation, which is xd square. Right, so now this whole term is dimensionless. I'm going to put all of this in a bracket, and then I'll put a negative sign around it. And then again, this bracket is not necessary. Close it in a bracket. Then I put in exp here. There we are. So we have a Gaussian. Is it double S? Zooming out. No, it's not double S. Okay. Gaussian space or Gaussian distribution. You just say distribution here. Right. Now we have the laser PG. It is equals to absorptivity, which is A1 in our parameters here, multiplied by the energy density multiplied by the Gaussian space. So this is the laser heat source. Right, so we have this laser heat source. Have we done enough? I think we have for now. Right, I'm going to move forward and create a geometry. Geometry, right click. We want to put in a rectangle, and everything, if we click on geometry, everything is in micron. So we set this, the width is W1 and the height is H1. build that, this is what we have. Right. So what we're going to have here is a laser beam moving from here to there. Okay? We're going to move on. And add and close this node. Now we're going to add a material. Our material that we created in the previous demonstration is in the user-defined library, and it is Alumina demo. Double clicking on it. This material, we were able to create a temperature-dependent density, temperature-dependent thermal conductivity, a temperature-dependent viscosity, surface tension, modulus of elasticity. We have even the heat capacity here. So essentially we have all these parameters that we want, or at least the material properties that are temperature dependent, which is what you want in the simulation, at least to improve its accuracy. Next, we're at the heat transfer node. So what we want here, we want to have, let me go back to geometry. We are going to say the laser beam is moving here along this top surface, meaning we insert a heat flux here, an inward heat flux. And then the laser beam or the surface is cooled, also the surface is exposed to the environment. On the sides and also at the top. Here at the bottom it is insulated, meaning it's sitting on the base of a surface. Very minimum heat losses. So, and also we have radiation losses right here, the surface, and there on the side as well, if the temperature is high enough. So, right-clicking on heat transfer, we add a heat flux, and we select the top surface, and the heat flux is exactly this Gaussian laser pulse, PG, which is a laser heat source. So I'm going to rename this heat flux, copy, laser heat source. And then the general inward heat flux, I'm going to write PG, the Gaussian laser pulse. Okay? Next, we add the convective cooling, which is also with the heat flux, and we rename that up there as cooling. The surface is cooling simultaneously as we irradiate with a laser beam, on the sides as well. So this is not going to be general inward heat flux. We're going to click here and check that box for convective heat flux. And the heat transfer coefficient is user-defined. It is H1. Remember that up here we have this as H1, the heat transfer coefficient, 10 watts per meter square Kelvin. This is a general equation. The beauty of COMSOL Multiphysics is that it has all the equations here, and you won't have to be guessing what the equations are. There's a general heat flux there, a heat transfer coefficient, and a temperature, external temperature, we called that TA, which is, under parameters, there, TA. And then the surface is also losing heat via radiation on all these boundaries except the bottom boundary. And there's the equation there. Expand this node. So the parameter to include is T ambient temperature and the emissivity. There, ambient, TA. And then emissivity, we say user defined. And we scroll down and we're going to write Emmy here there. Why Emmy? Because we said emissivity here is Emmy, 0.7. We're going to call this radiation losses. Right. We've defined the heat transfer parameters. Let us save the model. Next, we're going to mesh the surface. Let's build all. That's a coarse mesh. It's a normal coarse mesh, which is not ideal for the simulation. It may be quicker, but the simulation might not converge or it might not be accurate enough. You would want to have an extremely fine mesh. This will take longer to compute, but it is ideally that's what we want. But what I'm going to do is that I'm going to come here in the geometry. What we want to have at least this top part of the surface highly meshed, and then we can have a coarse mesh here at the bottom. So what I'll introduce is layers. Let's say make that D times 2. Or D, let's see what it looks like. Okay. So we're going to have a very fine mesh here at the top. And then here we're going to have a coarse mesh. This is just to simplify the computation for the software. Okay. Closing this node. I'm going to come here. I'm going to add a triangular mesh. Right click on triangular mesh and adding size. This mesh is applicable only for the domain at the top. And based on the article, when they describe their workflow, they emphasize that they use the mesh conditions, customized mesh conditions, which are maximum element size of 14 micron, minimum of 2 micron. So 14 and 2. If you build that mesh, see that it's very fine up there, which is what we want. Then let's add another triangular mesh, which is going to mesh the remaining surface. There. So we want to at least have an accurate computation here at the top. Here, not necessarily, but because an assumption is that the laser beam won't be getting to this level, the temperature, the heat. But we'll see. So next, let's save. So this is the time-dependent study. Let us add show default solver. What you want here is to change at least the time stepping, make it intermediate. You want to improve at least the chances of convergence in sample. You can force the computation to follow the time stepping, or at least give it some room to figure its way around the time stepping so that it finds the solution. Okay, so let's see if this simulation works. We're just going to give it dry run and see what happens. Compute. The simulation has completed. I had to change something a little bit. I had to make the mesh a little bit coarser so that the computation was a little bit faster. I changed here, made the mesh finer, and here I made the mesh extra fine and use a predefined option instead of customizing it. I'll customize it later once I've discovered that the simulation works as desired. So this is a typical outcome of the simulation. Let me just do this. I could make an animation here so that we can see that what is happening here. Let's put it on repeat and play it. So what is happening is that the beam is not pulsing. It is also not moving. However, it is at 1000 micron along the x-axis, obviously landing at the top of the surface. What we want to demonstrate really is a laser moving from here to there. I would actually want it to move it, start from outside and then come in and exit the sample. So what I'll do is to now modify the heat transfer equation, laser source equation, and make it a moving laser heat source instead of a fixed heat source, because right now it's a fixed heat source. It's more like we're drilling, really. And we're also going to include a surface probe or domain probe to quantify the surface temperatures. But right now it sits with the very high 1.2 to exponent times 10 to exponent 4. So stopping the player. So we're going to come here. What we did not include here is the laser scanning speed. So in this article that we're looking at, the scanning speed is 10 millimeters per second. So laser scan speed. So this is how fast the laser beam will be moving from here to there. So what I want to find out is how long will it take for the laser beam to move there so that I can calculate a computational time. So I'm going to say T stop. This is when the computation will stop. it should be the length of the laser beam of the surface divided by the speed of a laser beam. So that is width there divided by Vn. So it should take about 0.36 second. So let's say single pass duration or stop calculation. Stop computation. This should be computation should stop at 0.36. But since I want the beam to start outside, so the full beam, and finish, also meaning that it must exit there. So I'm going to add onto this path, and let's say 2 times the diameter of the laser beam. So it's going to be 0.48 second, meaning that outside to just 2 times the laser diameter. So it's going to start outside and go and exit outside. Or, well, finish outside the sample. Then what we need to now also do is to change here, modify a little bit the position XR. So if I modify XR there, let me just say, call this X0. Let's make that D. It's going to start at, let's say, minus D. Let it start outside the sample, minus diameter. So, of course, this is 0, this is the negative side. And then we're going to change XR to something else. I'm going to place XR here into an equation, which is X0 plus V in multiplied by T. So we are now including the scan speed here, meaning that we are forcing the laser beam to move. So this is the laser beam position, the transient position. So the beam is going to move based on this equation at this speed starting from x0. Now, obviously, automatically the laser heat source equation is going to be modified because the Gaussian space has XR, which is the moving laser beam. And then here, I would like to modify this as well and say, remember we said it must stop at T stop, right there, T stop. That's where the computational end, 0.48 seconds. So I'll copy that and put it there, 0.48 seconds. Let me make this, the time step, to be pulse width. Does it matter? Does it? Let's not change that. 0.48 second, I want this computation to be fast. 0.48 second, 0.1, it's going to be very coarse. Yeah. Okay, let's go 0.01. Nothing that's in ASCII. It's the time step. And then here, I'm not going to change that, but I'm going to delete it on purpose, and I'll reinsert it. This is to get rid of the previous computation. Time it stands in the way of the new data that is coming in with the new computation. Now, let us compute. Oh no, pause that again. What I forgot to add was the probe. We want to know what the temperature is on the surface. So I'm going to right click on definitions and add the probes, a domain probe. This domain probe is only going to measure, okay, fine, let it measure this temperature everywhere. But I want to know the maximum surface temperature. Not everything, just the maximum surface temperature. That's what I care about. Okay, so we can now compute. So as the computation happens, you see that the probe is giving us what the surface temperature is. You see that right there? So it's quite interesting. The max is going up to 12,000, stopping there at 13,000. Okay. So you can see that temperature increases and there's no pulsing effect yet. It's going to be remaining constant as time increases. So that's good. So the computation is completed. So you can see if we look at the probe plot, at this point you can see that the laser beam is outside the sample, right there. Then after that, it enters the sample and you can see the temperature increases and it's constant at 13,000. This here, it shows that our meshing is coarse and also our time step is not small enough. But we are at the moment we're still trying to figure out what if the model works. Right, so here we have the laser beam exiting the sample and temperature then drops. If we could come here and observe the animation, there it is. You see that? So our laser beam was able to move. If we could just put that on repeat, our laser beam entered the surface and very interesting. Cool. So it enters the surface and heats up the surface and it exits the sample. So I would like to say you have successfully modeled the moving laser heat source, a continuous laser heat source. Pause. So now, just to recap, to model a continuous laser heat source, we first inserted the laser parameters, which were standard deviation of a laser beam, the starting point of a laser heat source, the dimensions of the sample, the speed of a laser heat source, and the ambient temperature. We also had to insert the pulse energy, the pulse repetition rate, and the heat transfer coefficient. We also inserted the absorptivity. And then after that, we went to variables and we created or inserted the laser heat source equation. First, we defined the energy density by taking the pulse energy and dividing it with the pulse width and the area of the laser spot. If it is a different laser, you won't have to insert the pulse width. You could just simplify the pulse. I think in other lasers they use power if the laser beam is a continuous wave. So they use power there. You don't have to convert the pulse energy into power by dividing this by pulse width. It's already power. And then you can just simply divide by the spot area. So then you have watt per meter square, which is the heat flux. Then we defined the laser Gaussian space. And then we also defined the pulse or the laser heat source. And then we had to now incorporate the laser beam transient position by inputting the beam, let's say the laser scan speed, multiplying it with time, and adding that to the initial laser beam position, which is outside the laser spot. Or if it was inside, it was going to be a different value, but this is x0, which we defined as negative d, which is outside the the sample with just the diameter, the full diameter of the laser. And then after that, we created a geometry. We did it in such a way that the dimensions of the sample were dependent on the beam diameter so that we don't overestimate or over design the sample dimensions, and we over calculate, and we spend time doing calculations that were not going to help us, but at least if we are closer to the laser beam, we can get a better reading and a much quicker computation. And then this was our diameter, our sample. We created two layers, where one layer, the top layer, is highly meshed, and the bottom layer is not as highly meshed with a coarse mesh. We had to modify this mesh from a very fine mesh into just a coarse, or I would say, looking at the finer mesh, to just have a much quicker computational time. So in a way, this is a way of knowing that if the model works. And then after that, we inserted the material properties, and the material, which was alumina, which was we created in our earlier demonstrations. And then after that, we defined the heat transfer physics by inserting a heat flux to define the Gaussian laser heat source used at the top, the cooling effects by convection, and then radiation losses on the surface as well. And then we meshed, and then we have the computation. And if we look at the probe plot, we can even create an animation here, list 2 frames. Okay, we can do it after, fine. We can do it after we have made the computation finer. We had an animation here of the laser heat source or laser beam as it moves across the sample, which is a very good outcome. So now what we are going to do is modify the laser beam into a pulsed laser beam that is moving across the sample. What we want to achieve is, in a way, I'm going to zoom in here. We want to achieve this right here. Laser on, off, move, on, off, move. So we want to have such a temperature profile on the surface. I doubt that it's going to look as close as this, but because this is a fixed laser beam, it's not moving. But in a way, you want to have those peaks, heating and cooling effects, cooling cycles on the sample. So just to take an equation from this publication here, what they did was, let's come in here, zoom in here, there. They introduced this parameter beta here. Beta is rect mod, rect1 mod t, that's the period. So in a way, they used a square wave form and then they modulated it. So this is an analytic function. As they describe it here, they use an analytic function to combine everything. So we're going to do that as well. So let us try to create that. Under definitions, we are now creating a pulsed effect of a laser beam. Let us create a function, square or rectangular function, with a lower limit 0 and upper limit as pulse width, and we do not want to smoothen it. So there it is. The laser beam is on for a duration equivalent to the pulse width. Then after that, it is off. And then we're going to now add an analytic function. This analytic function, let's call it B, or let's say pulse, and call this B, and expression is, we call this a rectangular function, rect1, and what they did was to modulate the beam and say for a time and up to period, which is 1 over pulse frequency f, close these brackets. Our argument here is t, units in seconds, and let's see what happens. See that there's a lot of pulses here that are incident on the surface. So what we want is to have them stopping at t stop. Right, so we are going to have how many pulses? 1, 2, 3, 4, 5, at least 5 or 6 pulses on the surface. Okay. Now, what will happen if how will I include this into this model, into this Gaussian, into the Gaussian laser beam? Let's see if I say multiply by b, which is a function of time. Okay, so it is working, it's letting me do it. So now we are incorporating the movement of a laser beam by xr, and then we're also incorporating the pulsing effect of the laser beam, which is going to be very interesting. So we're now also going to change something. We want our time step to be very sensitive to the pulse width. So I'm going to change here to pulse width. Let's divide that at least by 2, so that at least we are accounting for the pulse width, because we don't want to have a time step that is greater than the pulse width. Okay. Now we are going to try and compute, but before we do that, let's delete the solvers. Delete the solvers, and this probe table is deleted as well. Clearing the data. Let's have another default solver with a intermediate time step. All right, let's see if we can compute this, if it works. Before you compute, just save first. I'm just going to save it because sometimes you don't want to lose all that work. Compute. Let's look at the probe plot for a few seconds. Okay, looks like it is not increasing because right now it should already, or maybe it's because it's outside the sample. Okay, let's wait for the calculation. Okay, the computation has completed. Let us see if we were successful in computing this pulsing, moving laser beam. Let us have a player file. Ooh, hi, hello, hi. Let us play this again. It is the coolest thing in the world. You see that right there? One. How many pulses is that? Jesus. It's the coolest thing in the world, isn't it? Right. So we're successful in doing this. But what is the temperature? Look at the probe plot. Do you see that? So the pulses as they land on the surface. It is the coolest thing in the world. So you have these pulses, the first pulse, the second pulse, the third pulse, the fourth pulse. So we were able to create 4 pulses landing on the surface. Brilliant. Okay, and now this probe plot. Are we able to animate it? Okay, let's see. Okay, right. That's laser pulse. We add a 1D plot. Will it be able to generate the frames? Add. Interesting. So you could see that you have on a line plot uh, the pulses are not overlapping as well. You see that there, the spacing between the pulses. So they're not overlapping. Is this animatable? It is, yes. Boom, boom, boom. Right. So either way, it's showing us that you have different lasers landing on the surface. And okay. Let's see if we can animate this probe plot. and to extract data from a domain probe, and then expression is temperature right player. Okay, so this is very interesting. So we were able to demonstrate two types of laser machining processes, which is continuous laser machining, which is more like a cutting, and then we have here the pulsed mode of the laser, which is could be used for laser texturing, marking, which delivers a more controlled dose of energy, which is quite interesting. So I would like to think that we have concluded our simulation, and thank you for watching our demonstration.